Οπότε μπορούμε να ξεκινήσουμε. Μεγάλη μας χαρά που έχουμε μαζί μας τον Πάτρη του Παπαμάνθου. Είναι επίκορος καθηγητής στο Πανεπιστήμιο του Μέριλαντ. Το διδακτορικό του είναι από τον Brown, αν θυμάμαι καλά. Και είναι πάρα πολύ ενεργός στο κομμάτι της κρυπτογραφίας, της ιδιωτικής επεξεργασίας δεδομένων και θα μας μιλήσει για κάποια από αυτά τα ενδιαφέροντα θέματα και για blockchain.
Thank you, Milos. Thank you very much for coming. Okay. Thanks a lot for coming this whole day. So yes, so my main area of research is cybersecurity. In particular, I focus on problems that have to do with cloud computing, security in cloud computing. But before I get into that, let me start with the basics. So traditionally, whenever we'll hear the word security and privacy, this is the picture that will come in our mind. So there will be two parties that typically will trust each other. We call them Alice and Bob, and they will like to communicate over an insecure channel, right? But unfortunately, there's this adversary that is sitting on this channel, and the adversary has two goals. First, to tamper with the information that is being exchanged, and to eavesdrop the communication. So, years of academic research have given us TLS, which is the protocol that runs in the background whenever we connect with HTTPS, right? And it is estimated that around 75% of the internet traffic runs over TLS, right? So, in that sense, my point is that in terms of point-to-point communication, securing point-to-point communication, we're doing pretty well, and this problem is pretty much, I would say, solved. So now you might have noticed, though, that we live in a different world, right? So we moved away from point-to-point communication to this new model of cloud computing, where you have parties that are interacting through this untrusted massive repositories like Google, Amazon, Dropbox, right? And just to give you some statistics, so Gmail is estimated to have around 1 billion users. Around 1.2 billion files are daily uploaded to Dropbox, and Amazon operates close to 1.3 million servers worldwide. Now, Ethereum blockchain has exceeded 1 terabyte of transaction data, and I'm not throwing blockchain here as a buzzword. You'll see there's many interesting problems that exist in this new domain. So, unfortunately, we're not doing very well in securing this type of systems, right? And you know, things do go wrong, and in particular, cloud data, like email data and Dropbox data and cloud computations can be corrupted. So this is one of the main problems. And cloud data can also leak to unauthorized parties. So we have identified two major problems. One is an integrity problem of cloud data and computation, and the other is a privacy problem. Okay, and do not take my word for that. If you do a simple Google search, you'll find multiple security incidents that all the way from accidental data losses, data breaches, and so on and so forth, right? And also many servers that actually justify the security incidents. It's not like random events, there's the consistency in this event showing up. Now I want to point out two things here. First, there's this interesting research that says that 80% of public cloud database remain unencrypted. Actually, recently there was again, so before I left the United States, there was again a data breach that took place, a massive one, right? So now, why there's this massive data breaches? So they asked this guy from Yahoo after the Yahoo data breach took place, and he said that, look, if we were to encrypt our data so that, if there's a data breach, we're protected, we could do that, but the problem is once you do that, you're losing all the capabilities of search and computation on this encrypted data, right? So this is one of the main problems, right? Okay, so these are all very interesting problems. So the bottom line is there's a lot of attacks, there's a lot of data breaches, there's integrity problems, privacy problems. And so in my group at the Maryland Cybersecurity Center, we use cryptography to secure data and computation in untrusted environments. This area is quite broad, and we're working across multiple thrusts. So first, we're looking into protocols. There's two kinds of protocols we're looking into in this domain. First, delegation of computation. How can you verify that a computation that is performed by an untrusted server returns the correct result? Second is privacy-preserving protocols. How can you encrypt your data and still be able, so that in a way that you're still able to do some computation over the encrypted data? This is actually work that I've been doing with Yanis that graduated from here. So another thing that I'm looking into, I was talking to Minos about that before, is attacks. So some of the protocols that we've been developing have this notion of, you know, if you are to be efficient, you have to leak certain amount of information. So this amount of information, this leakage, how they call it, was considered to be harmless. But, you know, we have looked into this more specifically and, you know, have developed various attacks that, so that we're able to de-anonymize data by just looking at this leakage. So another area that we're looking into is this notion of developing tools for non-cryptography experts. So we're developing all these verifiable computation searchable encryption protocols, but what's the use of all these protocols if only cryptography experts can use them, right? So what we're doing is we develop this front ends where you can write your program in a high-level programming language, and with a press of a button, you can actually create the secure cryptographic protocol, right? So that, you know, these protocols can also be used by non-cryptography experts. So we're looking into application. It turns out that blockchains right now is a fantastic vehicle to test these new protocols, right? So we have like various applications in privacy-preserving blockchains. We're looking into how we can make blockchains more practical by not requiring the miners to store so much information or to do so much computation. And finally, we're also developing systems that make direct use of these cryptographic protocols. In particular, recently I've been developing this Google Chrome plugin for Gmail, where it offers end-to-end encryption between users that are connected to Gmail, but at the same time allows someone to search over the Gmail inbox using searchable encryption, which otherwise would be impossible. Okay, so I'm going to talk a little bit about this project at the end. Of course, I'm not going to cover all of this. I'm just going to give you like a flavor of this work. So I'm going to talk a little bit about the most basic problem of verifying the integrity of untrusted storage. Then I'm going to move to verifiable computation, then some applications in blockchains. I'm going to talk a little bit about privacy, and then I'm going to finish with my project that I'm doing on privacy and search. So please feel free to ask me, to interrupt me if you have any questions. Okay. So one of the most fundamental problems that we looked in the beginning is how you can store your files remotely and still be able to make sure that whenever you read the file back, this file has not been changed. Okay, so it turns out that Dropbox provides you this. So you can basically store a hash locally along that corresponds to the file that is stored at Dropbox, right? And the protocol is very simple now. Whenever you want to verify that the file is intact, what you do is you download the actual file, you recompute the hash, and you check to see that this hash matches the locally stored hash. This is a very simple protocol. Okay, so when I was doing my PhD, actually I implemented these protocols. I played a lot with various optimizations. It turns out these are really, really fast because the crypto you can use for this is really, really cheap. Okay. So now the protocol that I presented before basically addresses a very small aspect of the problem. The more interesting problem is how you can verify that all your data are stored intact, right? Okay, so before it was only one file, how can we do the whole thing? Well, one approach is to just download everything using the previous protocol, right? And check every single file at once, every single file individually. Unfortunately, this is very, very inexpensive, right? So if you have like 5 gigabytes of data, in order to make sure that everything is in there, you have to download 5 gigabytes of data. This will not work. So the one approach that you might want to try is, say you have n initial files, and the server kind of tampers, it changes some bits in T out of this N files, right? So one natural way to think about this problem is, okay, instead of trying to check every single one of these files to eventually catch the server cheating, what I'm going to do is I'm going to pick like a random subset of these files, in particular C random, and I'm going to check to see whether this C random are intact, right? So if I'm lucky enough to pick the one that he has changed, right? So then I can know that something goes wrong, right? And then I can, have like say, I'm not going to use your service anymore because you are behaving dishonestly, right? So it turns out, so if you do the math here, so N is the total number of files, T is the number of files that the server is tampering with, and C is the random challenge that I'm sending. So it turns out, if you have like 1,000 files and T is 5, even if you try to do 60 challenges, the probability of you catching him is going to be 25%. So really, in order for this to work, you have to challenge a lot of files. So asymptotically, you have to challenge the linear number of files to have some reasonable guarantee. So this protocol is not really something that it's interesting to use, but it serves as a motivation of the solution I'm going to present next, right? So what you can do is you can use this notion of error correction. So again, you want to challenge a few number of files so that to catch some corruption that has happened at the file collection, right? So what you're going to do is, before you had only these N files that are being stored on the server, you're going to store another N files which are going to serve as error correction. So I'm in DC department, so I'm sure everybody knows about error correction. So the idea is here that, if you have two N error corrected files, right, so any subset of N plus 1 will be enough to reconstruct the initial N files, right? Okay, so basically for the server to cause actual damage to your files, he has to tamper with N files. So out of the 2N, he has to do a lot of damage, right? So, and if he does that, then there's no way you can reconstruct. Now, if you check only a constant number of files, then you can catch him, right? So this is the idea, right? So you increase the storage by error correction, you check a few number of files, and then you can compute the probability that you're going to catch the server with probability that grows exponentially with the number of challenges. Okay. So this is a protocol that was developed by other people, but then the problem with this protocol is when we started talking about this to companies, actually, they were very excited that you can actually have such a real world guarantee with very cheap communication. But the elephant in the room was the updates, right? So collections that are being stored at Dropbox are highly dynamic, right? So you want to support updates on these databases, right? And the problem is, if you're storing your database along with error correction, now if you say you want to append a file in your database, unfortunately this append will cause every single bit of error correction to change. So update becomes linear. That's not good, because the cost for saving one file will be at least linear, right? So we don't want that. So to have this guarantee of integrity checking for a dynamic set of files, you had to spend linear time for update. So we digged out a trick from data structures. It's a generic way to turn any static data structure to a dynamic one. We call it cascading tables. And the idea is, instead of actually updating the data structure and like the whole number of files, what you're going to do is you're going to have this exponentially increasing size of tables, and the first update will go in this table A. Now computing the error correction for this is very, very cheap. Now the second update will just move everything to B. Again, computing the error correction for this is a bit more expensive, but still not that expensive. Now the third update is very cheap. The fourth update is a little bit more expensive, but anyway, if you do that and you do the amortization, you will see that the audit cost, so the update cost is going to be log n. So this is amortized, the average, right? But here the audit cost, in the first solution it was, you had to check exactly C files, but here you have to check every single of these tables. So it's C times log n. Okay, so we're able to solve the update problem by just increasing the number of checks a little bit. And this login actually can be also sold to people worst case.
Does this work for deletes as well, or is this just for appends?
You have to treat deletes as appends, and you have to do some cleanup, but I don't know if you can use some existing techniques that handle deletion as well. I think I looked into that a little bit, and I don't know, is it possible? Because I'm sure like in databases you guys are looking into this.
I think there may be something, but
yeah,
that's not.
Yeah. So here is some kind of performance results. So on the left we saw how many bytes you have to upload when you're sending a 4096 bytes file to Dropbox. Left bar is no security, so when you have no security at all, it's exactly 4096 bytes, you're not sending anything else. Right? With our approach that offers this integrity checking guarantee, you have to send another 1.5 kilobytes. Right? So, and this basically comes from the login cost that I mentioned. Right? So it's not that bad. So we did pretty well actually. We filed a patent for this work. So we also got the Invention of the Year award at the University of Maryland. Here is me with my co-author, and here's the president of the university. So that was cool, right? And there's some companies that showed interest into actually commercialize this technology. It hasn't moved yet, but we're still in discussion. So let's see. So this was about the storage problem. Now I want to talk a little bit about a more complicated problem, which is verifying computation. And the problem there is how you can verify computation that is executed by an untrusted machine. Of course, you don't want to execute the computation yourself, right? Because this would require you to spend the same amount of work, so you don't want to do that. So you want to have something much cheaper, right? So, say for example, to give you a motivation here, say you have a database query. To execute join remotely takes linear time, but join may return like only a few tuples, 5 tuples. So you want to be able to verify that these tuples are the correct ones without having to spend linear time yourself. Okay. Now it turns out that for this problem, there is some technology that you can use. It's called CKeystart. Right? So you can go and download it from this GitHub repository, and let me give you like an idea of how this works. So you write the program that you want to verify in C, for example, and then there is a compiler that takes this program and feeds into a setup algorithm, right? So the program is fed into the setup algorithm, and the setup algorithm outputs 2 pieces of code. One is called proof.c, and the other is verify.c. Now, what proof.c does is running the program itself. So on input x is going to actually run the program that you feed in the beginning, and it's going to output this f of x. Right? But at the same time, it's going to output this bit string that is 288 bytes, which serves as a proof of correctness for f of x. Okay, so now x, f of x, and the proof are being sent to the verify algorithm, right? And the verify algorithm now can access these 3 elements, and it can either output accept or reject. Okay. So note here that the verify algorithm just runs in time proportional to the size of the output, right? So verify is really fast as opposed to proof. Now the guarantee of this, the security guarantee, is that if you output accept, the f of x needs to be correct, except with some negligible probability. So there is a chance that the prover might cheat, but the chance is extremely small, and it relates with the cryptographic assumptions that the system is using. Right? In other words, say if he's able to break RSA, then probably he's able to break the system as well. Right? This is the intuition. Right? So now, the interesting property here is that there is this notion, so the system comes with a switch that is called the zero knowledge switch, right? So zero knowledge has the following property. Basically, it says you can do the verification algorithm without actually seeing the input, which is kind of weird, right? So what will that mean, right? So if you turn the switch on, I can just give you an output, and what accept will mean is that f of x is a correct evaluation of the program in some input x that I'm not revealing to you, right? So it cannot be an arbitrary output, right? It's a correct evaluation of the initial program at some input I'm not revealing to you. And to think about this in terms of applications, think about, say for example, I'm giving you a ciphertext, right? And I want to prove to you that this is an RSA ciphertext. And you know, I don't want to reveal the secret key that I'm used to produce the ciphertext, right? So I can give you like a zero knowledge proof that will tell you, okay, trust me, I'm not giving you the key, but there is a key that I used to produce it. Right? So this is kind of the application, like the one-on-one application of this technology. Okay, so the reason that we've been working a lot on the zero knowledge proofs recently is because they have found a lot of applications on zero knowledge privacy preserving cryptocurrencies. So I'm sure you have heard about Bitcoin and all the cryptocurrencies. One of the problems, quote unquote, of Bitcoin and cryptocurrencies is that all the blockchain is public, so all the transactions are public to everyone. So it turns out that you can use the technology of zero knowledge proofs to build a cryptocurrency where no information about who sends money to whom and how much the transaction is will be revealed to the public. Okay. And actually, it's not like a theoretical thing. There is a cryptocurrency called Zero Cash, and you can buy actually these tokens that is using zero knowledge proofs to achieve complete privacy of the transactions on their blockchain, on the Zero Cash blockchain. I think now, I don't remember what's the price for one Zcash now. Yeah, I think that's up, it was $500. I don't know what's the price now. Okay.
So Bobby, good
Yes.
question. So what's the trade-off? So if I hide the input, does that mean that my prover and my verifier are much more expensive, or I mean, what's the trade-off?
Actually, it turns out that there is you can build zero knowledge with many different cryptographic primitives. There is the most prevalent one, which is the one that is used in Zero Cash actually, which is called quadratic arithmetic programs. The overhead of zero knowledge is nothing better. So it's just like you add some randomness in the way you're computing your proof, right? And this, I mean, you have to do something extra, but from a practical perspective, for this type of technology, the overhead is really minimal. I mean,
But this quadratic
arithmetic program,
that's a blow up over the original program. Right?
Oh, absolutely, yes.
Okay.
So,
but okay, but you're saying that you need to do that
for the zero knowledge. I thought you were asking about the zero knowledge over the verifiability. No, the verifiability has a lot of overhead. I'm going to talk about it.
Okay.
I'm talking about adding the switch, right? To the right. But for other technologies, adding the switch can be more expensive. So. So let me talk actually, I mean, this relates to what Minos asked about some of the challenges of the zero knowledge proof systems. So one of the challenges is that, remember, to output this proof algorithm, verify algorithm, you have to run the setup algorithm, right? And this setup algorithm has to be trusted. Not in all technologies, but the one I'm interested in here. I'm talking about here. What does it mean trusted, right? So there is a person that takes the program, picks some randomness, and you need to trust this guy that this randomness that he picked to output this proof C verified C, he's going to somehow forget and he's not going to reveal to anyone else, right? It's like a secret key that should never be revealed, right? But this is one-time trusted setup, right? So you do it, it's per program, right? So you do it for each program, but then once you produce proofs in verify C, you can verify multiple executions of the same program, right? So this is kind of a limitation of CKeystart. Actually, that was a big thing when they used it in this cryptocurrency, because the whole notion of being decentralized came at odds with this kind of trusted setup, right? Because they had to trust someone, so if they went over the top to find a way to run this trusted setup without having to. So there is some kind of secure multi-party computation. There's a YouTube video you might want to check. Actually, it's interesting, right? So one other thing is that comes back to what Lenos asked, is that the cryptographic cost that you have to spend to produce the proof is proportional to the size of the computation, right? So in particular, for every, if you think about the computation as a circuit with multiplication gates, right? So you have to do one exponentiation in an elliptic curve group per multiplication gate. So this is really, really many orders of magnitude overhead here. Right? So there's like the prover cost is really enormous, and I'm going to talk a little bit about that. So here is what I mean about that. So I'm referring to a specific technology now. So running this benchmark from a database on TPCH19 on a 6 million records using LeapSnark will just take 54 hours. Of course, we just estimated that for time. Okay. This is for if you use the technology that I saw before, this LeapSnark, right? There's other technologies for zero-knowledge proofs, including ones that I'm working on, that are doing a little bit better. They have some other trade-offs, right? So
how much of that is due to the data size, and how much of that is due to the proof itself? Is it primarily the data size that's the problem?
I would say half and half. So I mean,
So if I could reduce the footprint of the data dramatically, that would help?
Yes, because I mean the circuits also that is going to compute on the data will be smaller, right? Right. So
your circuit size is linear in the size of the data.
Yeah, because to run this quiz you have to express it as this circuit, right? So. So what we have been suggesting is this notion of universality, where the idea is instead of, so our work tries to address this. I mean, it's not solving everything, but it's trying to address these two problems that I mentioned. So we have developed a new zero-knowledge proof technique that says, okay, instead of taking as input the whole program, what I want as input is the size of the input of all possible programs that I will be able to support, right? So what I'm going to do is I'm going to give like, say I want to support SQL queries on databases of I don't know, 100,000 tuples, right? Right. So I'm just giving the size of the input. I run a single trusted setup now, right? That is going to spit out an untrusted setup, which is going to actually take the SQL query or the actual program, right? And this untrusted setup is going to output the proof C and verify C. So basically, this picture is similar to what I saw before, with the difference that the thing that is being fixed is the size of the input, and the program doesn't have to be fixed, right? I can change the program over and over again, right? Without having to do this trusted setup over time. Okay. So this is some series of work we'll have. Starting with like doing this for SQL queries. I was in Oakland 2017, and now we generalize from SQL to general computation. And recently, actually in August, my collaborator will present the final kind of version of this whole work in Crete 2019. So yeah. So let me tell you a little bit. So here, I mean, you give one program, you output proof C, verify C. If you give another program, then you can output another proof C and another verify C, right? And now the cryptographic cost is proportional to the input size, but not proportional to the size of the computation. Right? So this can cut basically the cost, the practical cost of the two, right? It can halve the practical cost. Okay. And we saw up to 120x savings. So I would like to give you a technical.
So I can do this but my database has to be N, or it can be smaller than N?
It can also be smaller than N, and you can pad, but you're going to have to pay the cost.
Oh, you're going to have to pad.
Yeah. I mean, you can do various things there with PowerShell 2, right? You can do like log n setups and stuff like that. Okay, so let me give you a little bit of a technical overview of how our approach works. So imagine you have a circuit at the client and a circuit at the server. And now the client wants to run a computation on the circuit, and he wants to actually verify that the output that is giving is returned by the server is correct. Okay. So he's going to say, okay, I have an input. Well, I don't want to run it myself because it takes too much time. Hey, what is the evaluation of the circuit that we have agreed on this input at 4, 3, 2, 1? Okay. So what the server is going to do is going to take the input, it's going to compute the first level, the second level, the third level, and it's going to get the output, and it's going to say, hey, this is 149. Now, bear with me for a moment, and let's denote with VIs the vectors of values at every layer of this circuit. Okay, so V0 is 149, V1 is 23, 126, V2, 114, 49. Right? So, a way for the server to convince that the output is 149, it is correct, is to do the following very naive protocol. First, I'm giving you V0, and then I'm giving you V1, right? And then I say, hey man, can you check to see if V0 and V1 are correctable, are consistent with the circuit we agree? So the client can do, okay, yes, I can run the circuit because we know we share the circuit. I can see that V0 and V1 is correct. Then I said V2, V3, and that's it. And then I can verify. Of course, now you're telling me, what are you doing? I mean, you're telling us that you're going to spend less time to verify, and you're running the computation basically, because you get something from the server and you verify. Well, this is just to motivate the next thing. Of course, the problem for this protocol is that it's not a verifiable computation protocol. It's a naive protocol that forces the client to do as much computation as the server did. So the main intuition here, which is based on interactive proofs, and the way interactive proofs work, it's an old idea, this interactive proof protocol, and the way it works is, okay, again I have this 4, 3, 2, 1 input, I send it to the server, now the server is going to do the same computation, and then it's going to come up with this vector. But he's not going to send the vectors back to me, but he's going to do something smarter now. So let's introduce some notation. If I give you a vector 3, 8, 2, 5, let me define this polynomial v of x, 3x cubed, 8x squared, 2x, so where the coefficients are the actual vector coefficients. Right? So now, instead of sending the vector itself, which is big, what I'm going to send is an evaluation of this polynomial at a random point that is being picked by the client. So client picks a random point R0, and server returns v of R0. So now, these polynomials are over a finite field, right? So an evaluation is going to be a fixed number of bits, right? So no matter how big the vector is, this is 256 bits, for example. Okay, so after you get V0 R0, you send R1, you get V1 R1. Right? So now, how can you check to see that V0 of R0 or V1 of R1 are consistent with the structure of the circuit? You don't have the vectors now so you can check. You just have evaluations of the vectors that you used. Well, I'm not going to go into that. There is a protocol that you can use that's called sum-check protocol that you can actually do that. Okay? And this is an efficient protocol that you can check that these evaluations are consistent with this circuit structure that you have. So this continues like this, and then V3 R3, and eventually R4, V4 R4, basically you need to verify that V4 R4 is the evaluation at your input. You can actually compute this and complete the problem. Right? So again, the main intuition is sending this evaluation. Now, this protocol was known before. What we did was the last part. So the last part requires that we compute an evaluation of V4 at a random point R4, where V4 is the actual input that we have, right? So what we did is basically say, okay, instead.
Sorry.
Yes.
So in this, you do have a possibility of failure because
yes,
it could collide.
Yes. So
for certain values.
yes. So there is a way that the server might convince us for a wrong result, right? So this probability is very small. It's 2 to the minus 60, and it depends on the size of the field, of the final field.
So it's basically collisions. So it
yes.
so happens that I picked a random thing that sort
yes,
of collides.
exactly. Remember, he cannot. I choose the randomness. This is very important. The client chooses the randomness,
Right.
right? And then he has to to send an evaluation of my randomness, right? So if he tries to seek me once, then the next randomness I'm gonna pick, he kind of he'll have to guess the next randomness I'm gonna pick in order to like keep fooling me. And for him to guess if it's like a 50 bits, 60 bits finite field, then it's the probability is to the minus 60. Right. Yes, so basically our main contribution was to figure out how we didn't want to do the last part, right? So what we did is we kept like an input digest. Instead of like keeping the input locally, we hashed the input and we say, okay, so instead of me computing the evaluation of my input, I asked him to compute the evaluation of my input, and then he also provided a proof that V4R4 is correct using another protocol that we developed. Right? So this actually allowed us to verify database queries, right? Because in this way we don't have to store the database, because the input in database queries, right, is the whole database, right? So what we kept is just a hash of the database, and we're able to verify arbitrary queries on a database hash that we have. So we use this work from signature of correct computation that I did when I was at Berkeley. We have to like extend it to run this last step significantly. So let me give you some results of this interactive proof line of work. So these are the numbers from LeapSnark. It's the 54 hours that I showed you before. Now, LeapSnark has very good verification complexity, right? It's only 6 milliseconds, and the proof size is really, really good, right? Now this is I showed just 2 queries there. Now, our work was able to go down to 1.3 hours. So this is from Auckland 2017, right? We increased the verification time a little bit, and we also increased the size. And now you're thinking, oh my God, I mean, this is still too expensive. It is, because native SQL, as you can see, runs at 6.67 seconds. But yes, I mean, this is the price you have to pay. I mean, of course, it's open research. I mean, we're trying to improve, but it's still terribly slow. I mean, this is the truth. Now, one light of hope, though, recently we were able to go from 1.3 hours to 20 minutes and 21 minutes. So this is actually the paper that my collaborator will present at Crypto in 2019. We call this zero knowledge proof system the Libra, but it's funny, it's not the Libra cryptocurrency, of course, by Facebook. We picked that name before the Libra cryptocurrency was announced. I don't know how we came up with it, but yeah, it was really fun. Anyway, so yeah, so we're able to go from 1.3 hours to 20 minutes. That means, you know, there might be more clever tricks that you can do to actually get this hopefully close to some practical spectrum. Okay. So I'm just going to highlight a little bit some other work that I've been doing on verifiable computation. So if you want, so I have this other line of work on verifiable computation where I'm considering specific functionalities instead of all possible programs or all possible circuits. And of course, if you constrain yourself on specific functionalities, you can do better. So let me give you some highlight here. So we're able to do, for example, when we started looking, we wanted to do shortest paths for graphs. Right? In the beginning, for 10,000 nodes, we were able to do it in 100 seconds. This was really, really bad, right? And then we have like some kind of other optimizations. Anyway, I'm not going to go into the details here. Eventually, we were able to go from 10 to the 8 seconds to 22 seconds using a bunch of various optimizations, in particular if we constrain ourselves in planar graphs. And the final thing that we did was a journal paper that we were able to do from 22 seconds to 21 seconds. Anyway, I'm not going to go into details here. I'd like to talk a little bit more about some other things. Okay, so let me talk a little bit about some applications of verifiable computation, in particular in the spectrum of cryptocurrencies. So let me just mention that the first work I did up applying zero-knowledge proofs into cryptocurrency blockchain was this hot work where we saw how you can do privacy-preserving smart contracts using zero-knowledge proofs, right? But today I'm not going to talk about this. I'm going to talk about something that I'm working on right now. But before I get done, let me give you like one slide introduction to cryptocurrencies. So Bitcoin was the first decentralized cryptocurrency and introduced this technology for maintaining a public transaction ledger in a distributed fashion. And the way Bitcoin works, and most of the other cryptocurrencies work right now, is you have like a Bitcoin wallet, so everybody can send transactions to the network. Right? And then there's these miners that actually store this database in a distributed fashion. They see transactions coming over the network and they decide whether a transaction is valid or not. If the transaction is valid, it's being added to the blockchain, right? It becomes part of the history of the system and nobody can remove it. Okay. And you can go to blockchain.com and you can see all transactions that have taken place since Bitcoin was launched in January 2009. Okay. So let's talk a little bit about the storage and computations in cryptocurrency. So it turns out that this is quite challenging. Storage that miners have, the amount of information that miners have to store in order to validate transactions increases in this way. I mean, right now I think it's around 160,000 megabytes, and it's going on and on. So this has multiple problems. For example, if someone wants to enter the system, right, he has to like wait forever to download this massive blockchain, right? So it takes forever to actually start validating transactions, right? One other interesting thing is because this storage is so huge, it has to go on disk. And in Ethereum, which is the cryptocurrency for smart contracts, where you can introduce computation, more complicated computation for the miners, you can actually craft transactions in an adversarial manner so that you can make miners access this more and more often. And actually in Ethereum there was such an attack in 2016 where they issued transactions so that would require miners to do random access on disk, and then the network completely stopped working. Okay. So all of this has to do with the fact that they have to store this information somehow. Right? So there have been a lot of discussion about the stateless client concept in the Ethereum community, so how you can still be able to verify transactions without having to store this massive amount of information. Okay, and this is the project I'm working on right now. So to understand how our idea works, let me give you a little bit an overview of how things work right now. So in Ethereum, you have miners that store the account balances of every account in Ethereum. So here, address A has 8 Ethereum, address B has 5 Ethereum, right? And then there's a client that wants to do a transaction saying, send 7 Ethereum from A to E. You send this transaction to the miners. Now, the miners have to do two things. First, they have to check that A has at least 7 Ethereum. And second, once this is the case, they have to go ahead and update the balances. Okay, so what they're going to do is, if everything is okay and A has the required amount, in this case, this transaction will be made part of the blockchain, right? And then the account balances will change. Now, our goal is this huge array of balances creates all the problems that we talked about, right? So we would like to somehow shrink that. Okay, so the idea is, instead of holding this account of balances, we're going to build this Merkle hash tree on top of this account, right? So we squeeze all this big array to a single digest R, right? So X is the hash of the accounts of A and B, Y is the hash of accounts C and D, and this hash is computed recursively after the root. So the miners now, instead of holding this whole tree, they just need to store this single root hash that represents all the accounts. Now, how can they verify transactions? Well, if I want to send some Ethereum and B and I want to send Ethereum to G through Ethereum, what I want to also provide in my transaction is a proof that my balance is, say, 4, right? So I want to give a proof of my specific balance, right? And if the miner verifies my proof and says that, okay, this guy has 4 because he just proved it to me using this proof, and I can verify this proof because I know this digest, okay, that means that this transaction is valid, right? And this transaction can be part of the blockchain. Now, there is a problem there, though. The problem is that I told you how to do number 1 of what miners have to do. Number 2, like I said before, is they have to update the balances as well, right? But again, they don't store the balances. So how are they going to update them, right? So the idea is that if I give a proof of the balance, I can also have him use this proof to update my balance. So this is easy, actually. Now, the question is how he's going to update the balance of the person I'm sending money to. Because he doesn't have any proof for his balance. And you know, the way Bitcoin works, I mean, when I want to send money to you, I'm not going to bother you at all. I don't want you to send anything to the miners, right? When I want to send money to you, I'm just doing a transaction, and he needs to find a way to update balances, right? And you know, he cannot go back to you and ask you about the balance, right? So the fundamental question that we have to address in this problem was how you can update the digest of a hash tree by accessing only the delta of the update. So I want 3 pieces of information: how much money I'm sending, who is the sender, and who is the recipient. And I have this hash of the digest of my hash tree, and I want to update this operation. So it turns out that there was some work that we had done in the past. Actually, when I was at Berkeley, we did this work on streaming authenticated data structures, where you could use actually this notion there to update this hash. But it turns out this was very, very impractical. There was also some other work, vector commitments that we could use, but again, it was very impractical. So the paper on the left was based on lattices, total, you know, it was slow. Paper on the right had some quadratic costs involved, so it wouldn't work. So we came up with a new vector commitment scheme. And here I'm showing some results of applying our new vector commitment scheme in this problem. So, so we call it EDRAX, this new work that we have. So here you see like the stateful verification. The red line is how you verify transactions when you store the balances on the disk, right? And here it turns out the experiments we did, because you have to store things on the disk, things started getting really slow after a certain number of accounts, right? Whereas in our case, we have a constant verification time because we didn't have to access this to actually validate transactions. Right? Of course, there is some trade-offs here. We have to add something to the transaction, right? So the proof size, we increase the size of the transaction. We have some work right now that we're trying to use zero-knowledge proofs actually to make this transaction very, very small. So this new algebraic trees that we use for this project are available on GitHub as well.
Sorry, so there's no, so you're saying that this line goes constant throughout the, isn't there like a log cost?
Yes, it is, but it's not,
so you still need to update the entire path, right?
Yes, it's a low cost. It's a low cost. But you know, because everything fits in memory, I mean, you don't have any. Okay, so I talked about some proofs, some verifiable computation. Let me just touch a little bit on privacy now. So, like I said, one other problem is this notion of encryption. So, if you want to keep your files private when you send them online, what you can do is you can send them to the server and just encrypt them, right? But then the problem is when you want to do a query on the data, so for example, give me all the encrypted files that contain a specific keyword, right? Because the files are encrypted, server just sees random bits, cannot do any query processing, right? And then the question is how to search your encrypted data. The idea is this notion of searchable encryption that actually Minos and Giannis have worked on. So searchable encryption allows you basically to take the set of files, you turn it into an encrypted index along with encrypted files, and now you send it over to the cloud. Now instead of sending the actual keyword, you're going to send a token, which is a deterministic version of this keyword that has been computed in a way that is compatible with this encrypted index, so that the server can use it to output pointers to the encrypted files that contain the keyword that is masked under this deterministic function, right? And then you get back the encrypted files. Now, this is the most practical way to do some form of computation on encrypted data right now. Unfortunately, this comes at a cost, and this leaks a lot of information, which can be really, really bad. But if we're willing to accept the leakage, then this provides some notion of privacy. Yeah, so it has been actually implemented by various startups, and some startups have also been acquired by McAfee, so that shows the potential of this technology. So I've been doing a lot of work on searchable encryption. I've been working on dynamic searchable encryption, so for example, how you can update the collection of files without leaking too much information. I've been working, actually, this work I did with Yanis on searchable encryption with good blockade. Actually, this work that I did it because of Yanis. Without Yanis, probably I wouldn't have gotten into this field. So the idea there is, so if you put your encrypted database in memory, right? On disk, right? You have like a massive encrypted database and you put it on disk. If you use a traditional searchable encryption scheme, for security purposes, this traditional searchable encryption scheme does a lot of random accesses, right, on the disk, right? So if you have it, if it's in memory, it's fine, but if it goes on disk, then you are in big trouble, okay? So the question is, so with Yanis we developed this new scheme, searchable encryption scheme, that have good locality, right? Instead of, if you want to access, like, say, like 100 tuples, right? You don't have to do 100 random accesses, you have to do, say, 5 random accesses, and then you go sequentially, accessing lots of things sequentially. So there's a lot of interesting practical and theoretical trade-offs there that we studied. Yeah, and well, so like I said before, there's leakage, so we have also done attacks and defenses for this leakage. Finally, I'll talk to you a little bit about this project that I'm doing with my undergrads at Maryland. So we're developing this plugin for Gmail, but using searchable encryption. We want to provide end-to-end encryption. So if you install my plugin, you can communicate with you can send emails over Gmail, but Google will not get to see the content of your email, right? And of course, you can do that. This is what WhatsApp is doing, for example, right? It encrypts the messages, right? But then, if you just stop there, you won't be able to use the search inbox, like the search functionality anymore. So what we did on top of the end-to-end encryption, we added the searchable encryption technology. And the way it works, of course, we couldn't add the searchable encryption at Google because we couldn't change the code there. So we have this encrypted index running on Amazon ECE TUC, right? So the idea is you send the keyword token you want to search for to Amazon. Amazon gets you the matching IDs, and then you send the matching IDs to Google, and you get back the encrypted emails from Google. Okay, so this is just a beta version right now. There's a lot of work to be done there in terms of system questions and how to deal with the leakage, and it's very interesting. Okay, so let me give you a little bit about my vision for the future. I think it's a very exciting time to work on cryptography. So we moved away from TLS and disk encryption to really advanced cryptography, right? So things that like zero knowledge proofs, secure computation, searchable encryption, fully homomorphic encryption, that used to be really science fiction 10 years ago, now we see them being deployed in real world systems like blockchains and so on and so forth, right? So yeah, this is really nice. I mean, this actually comes with big responsibility though. Let me give you an example here. I think it was back in February where there was like a bug that was discovered in the zero knowledge proofs that were being used in Zerocache. And it was discovered, this bug, in February, and people don't know if anybody had actually exploited this bug. And if you were able to exploit this bug, you were able to create money out of thin air. Right? So you know, have to be really, you know, if you are to use this cryptographic systems for money and blockchain application, you have to be really careful. So the goal is to design new cryptography with practical applications in mind. To give you an outline of some future projects that I plan to pursue, application specific for computation, how you can focus on more specific tasks like machine learning, more scalable blockchains. I saw a protocol that doesn't replicate storage. If you go to smart contracts, I don't want to replicate computation now. Right? So how we can use this verifiable computation and all those proofs in this domain. Privacy preserving smart contracts, how you can build a system that has no trusted setup. Hawk that we had before has a per contract trusted setup. We want to avoid that. This is not good. Right? We plan to study foundations of leakage and attacks, and defenses for searchable encryption, and more expressive end-to-end searchable encryption. The email project is only search, keyword search, how you can do like more conjunctive keyword search, more complicated searches. And so yeah, this, thank you.
Ωραία πράγματα. Κρίμα που δεν έχουμε περισσότερο κόσμο.